The space shuttle is unlike any other aircraft. In orbit, it functions as a spaceship. In the Earth's atmosphere, it flies like an airplane, descending along a steep glide path during its approach and landing. Because the shuttle is a multifunctional vehicle with unique handling characteristics, it takes specialized training to fly it. In order to train pilots to fly the orbiter's approach and landing phases, NASA developed a realistic flying trainer. A flying trainer was preferred over a ground simulator. Ground simulators, even with their high-fidelity computer graphics, cannot realistically reproduce certain aspects of flying. Characteristics like visual textures, shadows, depth perception, and the sensation of motion are essential to pilots. To experience these, you must take to the air. NASA responded to this challenge with the Shuttle Training Aircraft, or STA. There are presently 3 STAs in operation. From the outside, the STA looks like a standard Gulfstream G2 corporate jet, but it's been extensively modified. With these modifications, the STA can realistically simulate the orbiter's flight characteristics. Making the G2 feel, handle, and react like the orbiter took some ingenuity. Engineers have found ways to induce enough drag on the G2 to enable it to descend like the orbiter. The orbiter's steep descent along a 19-degree glide slope at 290 knots is quite different from that of an ordinary airplane. In order to make the smaller G2 descend like the shuttle, engineers have redesigned the thrust reversers to reverse in flight. This adds the drag necessary to simulate the orbiter's steep descent. The main landing gear has also been modified. Now able to extend while in flight, the main landing gear acts as a speed brake to increase drag. The designers next had to simulate the orbiter's response to pitch inputs, which are different from that of a normal airplane. In an airplane, the center of rotation is in the middle. This causes the pilot to feel a rising sensation whenever the nose of the aircraft rises. The center of rotation in the orbiter, however, is at the front, so the pilot feels a falling sensation when the nose rises. To simulate this feeling, the Gulfstream's aero surfaces have been modified with direct lift control, or DLC. The DLC causes the flap and flaperon to work together. The flaps on the STA can move up or down at 50 degrees per second, simulating the movement of the orbiter. The flaperons can be used as conventional landing flaps or with the ailerons for roll control. A typical STA training flight consists of repeated approaches, go-arounds, and climb-outs at high engine power. The steep descent and the reverse thrust of the engines, plus the repeated cycling of the landing gear, puts the aircraft through a lot of stress. The heavy stress endured by the STA requires the G2's engine pylon area, inboard trailing wing edge, and the aft fuselage area to be structurally reinforced. A more obvious difference between the STA and the unmodified G2 can be found in the cockpit. The right side of the STA cockpit houses conventional airplane controls, along with instruments for monitoring the simulated approaches. The left side of the cockpit has been equipped with instruments and controls like those in the orbiter. One modification is the rotational hand controller, also known as the RHC. The RHC is used by the astronaut to fly the STA the same as the orbiter. Moving the RHC generates signals that represent roll and pitch movements. The signals are fed into the onboard computer, known as ADAS, the Advanced Digital Avionics System. ADAS translates the astronaut's hand movements and electronically moves the aero surfaces to the desired positions. ADAS then checks the aircraft to verify those movements. If a correction is called for, ADAS makes the adjustment within milliseconds. The ADAS is also programmed with information about runway locations. Data such as present position, altitude, and airspeed are continuously updated and used to calculate the approach and landing path to the runway. There is also a multifunctional CRT display system called the MCDS. The MCDS displays vertical and horizontal situation data in the same manner it would appear on the orbiter's display monitors. To the astronaut's left is a speed brake thrust controller, which is linked to the ADAS computer. When the speed brake handle is moved, the ADAS is signaled to change the reverse thrust level. This affects drag and airspeed, the same as the orbiter's speed brake. One of the more important instruments in the cockpit is the heads-up display, commonly known as the HUD. The HUD projects a transparent image in the pilot's line of sight. The pilot aligns the projected image with the runway and guides the STA according to the display. The STA has a HUD for both the student and the instructor. Although astronauts are experienced pilots, they must learn a new concept of landing to fly the orbiter. Landing in the orbiter can be compared to flying a 100-ton glider to dead stick landing. The STA, with its modifications, is able to simulate this effect. Let's take a look at what happens during a simulation flight in the STA. Most STA training flights are conducted at the White Sands Missile Range in New Mexico. Astronauts are also trained at the actual shuttle landing sites at Kennedy Space Center in Florida and Edwards Air Force Base in California. A simulation flight in the STA begins on the ground. 2 hours before takeoff, the Flight Simulation Engineer, or FSE, conducts an extensive pre-flight checkout and preparation of the aircraft. Since the STA can fly like the orbiter and a conventional airplane, the FSC must ensure that both modes are pre-flight tested. While the FSC is busy with pre-flight, the instructor pilot briefs the astronaut about the simulation's flight profile and other pertinent information. Once pre-flight activities are concluded, the crew boards the aircraft. The astronaut sits in the left-hand seat and the instructor pilot sits in the right. From this position, the instructor doubles as safety pilot. The instructor pilot can terminate the simulation at any time. The FSC is seated in the jump seat between the astronaut and the instructor. Once the crew is aboard, the STA takes off. During the flight to the training area, the crew performs pre-sim entry procedures. Masks are inserted into the cockpit windows to simulate the view from the shuttle cockpit. Communications instruments, flaps, engine controls, and cabin pressure are adjusted to the proper configuration. The pre-sim procedures should be completed by the time the STA reaches its desired altitude. Once at this altitude, the pilot slows the plane to roughly 250 knots and performs the sim entry procedure. The main landing gear is lowered, the throttle is set, the thrust reversers and ADAS computer are engaged, and the DLC is checked to make sure it's in track. Each step of the procedure is verified by the FSE. Once the STA is in the simulation mode, the instructor transfers control of the aircraft to the astronaut. During the simulation, the instructor monitors the overall safety and execution of the approach, while the FSC makes all calls to the astronaut. In order to better understand how the STA simulates the orbiter's approach, let's look at an actual shuttle descent. The approach begins as a steep dive. Flying at 290 knots, the orbiter descends along a 17 to 19 degree angle at a rate of approximately 15,000 feet per minute. Its target is a point 7,500 feet short of the runway. At an altitude of 1,700 feet, the pilot begins a pre-flare maneuver to decrease the rate of descent. This transition places the orbiter approximately 1 mile from the runway on a 1.5 degree glide slope. After a final flare, the orbiter touches down with a vertical velocity between 1 to 3 feet per second. The STA simulates this profile in the following manner.
Pre-flare start. Roger. 1,000, 295. 500, speed brakes, 24, 400, 280. Here. 300, 275. 200, 260. 100, 245, 75, 240. 50, 40, 220, 30, 215, 20, 210, 10, 12, 5, 5, 2, touchdown. 510, please. 10.
The STA does not actually land during a simulation because the plane's wheels must remain 20 feet from the ground in order for its cockpit height to equal that of the orbiter. At 20 feet, touchdown is called out, and the instructor presses the sim exit button. This takes the STA out of its simulation mode. The landing gear is then retracted as the aircraft picks up speed and begins climbing for another simulation. A typical STA training flight consists of 10 approaches. An astronaut must fly more than 500 approaches in the STA before attempting an actual landing in the orbiter. At least 20 flights must be flown along the intended profile to the planned landing site of that particular mission. The Shuttle Training Aircraft is an invaluable part of astronaut training. At the end of a mission, when the orbiter is racing toward touchdown, there is no margin for error and no go-arounds. The importance of the many hours spent in the STA are realized with each successful shuttle landing.